Do you believe in extraterrestrials? Well, wait, don't answer right away. I know the question may seem strange, but it's more logical than it appears. Look at the sky for a moment. The universe is absolutely immense, potentially infinite. Our galaxy contains 200 to 400 billion stars, and there are 2,000 billion galaxies in the observable universe. Dizzying numbers. So according to this principle, if Earth can harbor life, why couldn't it appear elsewhere? For a very long time, most scientists were convinced that yes, and perhaps you were too. But today, I'm going to propose an idea that will seem crazy to you, perhaps even provocative or depressing. We are probably alone in the universe, completely alone. I'm not just talking about our solar system or even our galaxy. I'm talking about the observable universe, thousands of billions of galaxies, each containing hundreds of billions of stars. And we would be the only conscious beings contemplating this cosmic spectacle. It may seem absurd, yet that is increasingly what recent scientific advances suggest. The more we learn about the conditions necessary for a planet to harbor life, and the more we realize how much our existence is a statistical miracle. In this video, I'm going to take you on a dizzying journey through all the cosmic filters that make life so difficult and unlikely. We will start from a 100% probability that life exists elsewhere, and we'll see how the various discoveries we've made in recent years are changing this statistic. Anyway, I warn you, what you're about to discover could fundamentally change your view of our place in the universe. You will never look at the night sky the same way again. So before diving into our probability calculation, let me tell you about a paradox that has haunted astronomers for decades, the Fermi Paradox. One day in 1950, physicist Enrico Fermi was having lunch with his colleagues at Los Alamos National Laboratory. The conversation drifted to extraterrestrials, and suddenly Fermi asked a disarmingly simple question. But where are they? This innocuous question actually hides a deeper paradox. Let me explain. Our galaxy has been around for about 13.6 billion years, and our solar system is only 4.5 billion years old. This means other civilizations could have emerged billions of years before us. Even accounting for the limitations of the speed of light, a technologically advanced civilization could have colonized our entire galaxy in just a few million years, which is a blink of an eye on a cosmic scale. So, where are they? Why haven't we detected any signal, any megastructure, any interstellar probe? Why this radio silence? Why no visits, I've long been fascinated by this question. Like many, I would have liked a universe teeming with life and diverse civilizations communicating across interstellar space. But the more I studied this paradox, the more a response imposed itself on me. A response I wasn't necessarily willing to accept. They aren't there because they don't exist. Of course, other explanations can be proposed. Perhaps advanced civilizations are hiding. Perhaps they communicate in a way we cannot detect. Perhaps they systematically self-destruct before reaching the stars. But the simplest answer, one that requires no extra hypothesis, is that we are alone in understanding why. We must examine what is called the Drake equation. In 1961, astronomer Frank Drake proposed an equation to estimate the number of extraterrestrial civilizations in our galaxy with which we could communicate. This equation takes into account several factors: the rate of star formation, the fraction of stars with planets, the average number of planets potentially habitable per system, the fraction of those planets that could harbor life, and therefore by extension harbor intelligent life forms. The problem is that we don't know the exact value of most of these factors, and that's where things get interesting. In the 1960s, scientists were rather optimistic and thought that life was relatively common in the universe. But over the decades, as our understanding has refined, we began to realize that each of these factors could be much, much, much smaller than we initially thought. And if we take the most recent and most cautious estimates for each factor, what happens? Well, the number of civilizations in our galaxy collapses. It could even be less than one. In other words, everything points to us being alone. But don't take my word for it. Let's do the math together, step by step, and see where it leads us. Now I'm going to propose a slightly different approach. Instead of using the Drake equation directly, we'll start from a probability of 100%. That is, an absolute certainty that life exists absolutely everywhere, and see how this probability decreases as we take different cosmic filters into account. 100% is our starting point, the hypothesis that intelligent life is guaranteed to exist elsewhere in the universe. At each step of our reasoning, we will see this percentage decrease, sometimes even more dramatically. Let's start with the broadest filter, position in the galaxy. You've probably heard of the habitable zone around a star, this region, where a planet is neither too hot nor too cold to harbor liquid water. But did you know that there is also a galactic habitable zone? Our galaxy, the Milky Way, is not uniformly hospitable to life. In fact, most of its 200 to 400 billion stars are located in regions where complex life would have enormous difficulty establishing itself. Approach the galactic center, and you'll find yourself in a chaotic and deadly environment. The stars there are so densely concentrated that planetary orbits would be constantly disrupted. Supernovae explode frequently, sterilizing entire systems with their radiation. Black holes, including the supermassive Sagittarius A times at the very center of our galaxy, emit intense radiation and devour anything that gets too close. Move too far toward the outer edges, and you face another problem: low metallicity. Stars there contain very few heavy elements, the very elements that are essential for forming rocky planets like Earth. The galactic habitable zone is estimated to be about 10% of our galaxy's volume, a thin annular band located at a just right distance from the center. Our sun lies precisely in this zone, in a spiral arm called the Orion Arm, about 27,000 light-years from the galactic center. So think about it for a moment. Of the hundreds of billions of stars in our galaxy, only about 10% are in this privileged zone. Our probability has just dropped from 100% to 10%. But wait, not all galaxies are like ours. Some are elliptical, others irregular. Some are colliding, others are forming. The Milky Way is a large spiral galaxy with adequate metallicity and a relatively low rate of catastrophic events. If we estimate that only 10% of galaxies have similar characteristics to ours, our probability drops further from 10% to 1%. And that's not all. Our galaxy is located in a relatively isolated region of the universe, far from galactic clusters where collisions and disturbances are frequent. This privileged position is not the norm. It is estimated that only 10% of adequate galaxies are in a sufficiently calm environment. So our probability drops again, from 1% to 0.1%. You see where I'm going with this? We have only considered the first filter, the position in the universe on a large scale, and our probability has already dropped from 100% to 0.1%, and we haven't even started talking about individual stars and planets, or even the conditions necessary for a planet to host life. Let's zoom in now and examine our position in our solar system. The famous stellar habitable zone, also called the Goldilocks zone. This habitable zone around a star is defined as the region where a planet can maintain liquid on its surface. Too close to the star, water evaporates. Think, for example, of Venus with its hellish greenhouse effect at 470 degrees. Too far and water freezes completely, like on Mars or the icy moons of Jupiter and Saturn. For our Sun, this zone extends approximately from 0.95 to 1.4 astronomical units. An astronomical unit represents the Earth-Sun distance, about 150 million kilometers. Earth is exactly at 1 unit, almost perfectly in the middle of the habitable zone. But be careful, this zone is incredibly narrow. If Earth were at 0.9 astronomical units, just 10% closer, we would have an uncontrollable greenhouse effect, like on Venus. If we were at 1.5 astronomical units, just 50% farther, we would be an icy world. Across the entire solar system, this zone represents a tiny fraction of the total volume. Take a moment to visualize this. Imagine our solar system as a football field. If the sun is at the center of the field, the habitable zone would be just a thin strip a few centimeters wide. It is within this incredibly narrow band that Earth orbits, neither too close nor too far, perfectly positioned. If we consider that the habitable zone represents about 5% of the potential orbital volume of planets in a solar system, our probability drops again, going from 0.1% to 0.05%. But that's not all. This habitable zone is not static. It moves over the course of a star's life. When a star ages, it becomes brighter, and the habitable zone gradually moves outward. For a planet to remain habitable for billions of years, it must not only be in the current habitable zone, but stay there long enough. Our Sun is particularly stable. It is a G-type star of average size, not too massive, because stars that are too massive burn their fuel too quickly and explode after only a few million years. But also not too small, because red dwarf stars, though much longer lived, bombard their nearby planets with deadly radiation. And you know what's crazy? It's that G-type stars like our Sun only make up about 7.5% of the stars in our galaxy. The vast majority of stars are red dwarfs, smaller and cooler, whose habitable zones are so close to the star that planets there experience extreme tidal forces and devastating stellar flares. And among these G-type stars, only a fraction have the stability and age necessary to host a form of life. If we estimate that only 20% of G-type stars are sufficiently stable and old, our probability drops again, from 0.05 to 0.00075 for another crucial factor, the planet's orbit. Earth follows a nearly perfectly circular orbit around the Sunday. This circularity is essential to maintain a relatively constant temperature throughout the year. An overly elliptical orbit would cause the planet to alternate between too close and too far from the Sunday, creating extreme temperature variations incompatible with life. Highly circular orbits like Earth's are relatively rare, and if we estimate that only 10% of planets in the habitable zone have sufficiently circular orbits, our probability drops further. We are already at less than 1/1,000,000th of our initial probability, and we haven't even talked about the specific characteristics of our solar system, like the presence of Jupiter or our moon, which are absolutely crucial for life on Earth. Now that we've seen the importance of our position in the galaxy and around our star, let's now focus on the particular configuration of our solar system. Because with an ideal position without its cosmic guardians, life on Earth could never have existed. Let's start with Jupiter, this gas giant that is 318 times the mass of Earth. Jupiter plays a crucial role that astronomers sometimes call the cosmic vacuum cleaner. Thanks to its immense gravity, Jupiter captures or deflects a large number of asteroids and comets that would otherwise regularly bombard Earth. To give you an idea of the importance of this protection, look at the Moon and its countless craters. Without Jupiter, Earth would suffer much more frequent devastating impacts. A single major impact can cause a mass extinction, for example, that of the dinosaurs. Impacts too frequent could simply prevent Earth from being able to host life. But beware, Jupiter's position is just as important as its existence. Computer simulations have shown that if Jupiter were closer to the Sun, it would have disrupted Earth's orbit, making it unstable. If Jupiter were farther away, its protection against impacts would be insufficient. Planetary systems with a gas giant like Jupiter, located at the right distance from its star, are relatively rare. Exoplanet observations have noted that many systems have hot Jupiters. Gas giants very close to their star migrated inward, sweeping everything in their path. If we estimate that only 10% of planetary systems have a configuration similar to ours, with a well-placed gas giant, our probability drops again. But the most important guardian of life on Earth is perhaps our Moon. Our natural satellite is exceptionally large compared to the size of its planet. The Moon-to-Earth size ratio is by far the highest in the solar system, except for Pluto and Charon, which are rather considered a double dwarf planet. This massive moon plays several absolutely crucial roles for life on Earth. First, it stabilizes Earth's rotation axis. Without the moon, the tilt of our planet would vary chaotically over periods of about 1,000,000 years. Ranging from 0 to 85 degrees Celsius, imagine a day where the pole points directly toward the sun, creating extreme seasons. One half of the planet is permanently in glacial night, while the other burns under the constant sun. About 1,000,000 years later, no seasons at all. These extreme climate variations would have made life impossible on our planet. Secondly, the moon has significantly slowed Earth's rotation through tidal effects. Without it, our planet would rotate much faster, with days of only about 8 hours, which would cause catastrophic surface winds of over 300 kilometers per hour, making life practically impossible. So, how did our moon form? Through an event of staggering improbability, the collision of the proto-Earth with a Mars-sized object named Theia about 4.5 billion years ago. This collision had to be perfectly calibrated. Too violent and both bodies would have been pulverized, not enough, and they would not have merged properly. Moreover, the impact angle had to be precise to create a stable Earth-Moon system. Imagine the cosmic precision required. It's like throwing two marbles across a room, and they must meet exactly at the right angle and speed to form a stable system. Moons of relative size to ours, formed by such precisely calibrated impacts, are extremely rare. Very generously estimated, only 1% of terrestrial planets in the habitable zone have a satellite as massive and perfectly positioned. Our probability drops further. We are now at less than 1/1000th of our initial probability. And we haven't even talked about the unique geological features of Earth itself. I will now tell you about one of the most extraordinary aspects of our planet, plate tectonics, and its protective magnetic field. Earth possesses two extraordinary systems that radically distinguish it from other rocky planets in our solar system. Let's start with plate tectonics. Our Earth's crust is divided into about 20 plates that float on the semi-liquid mantle below. These plates move slowly, a few centimeters per year, creating mountain ranges when they meet, and ocean trenches when one dives under the other, and new crust when they move apart. This phenomenon may seem ordinary, but in reality it is extremely rare, because no terrestrial planet in our solar system has plate tectonics. Venus, Mars, and Mercury all have a monolithic crust, a single plate covering the entire planet. Why is plate tectonics so crucial for a planet that harbors life? Well, for several fundamental reasons. Firstly, it acts as a planetary thermostat by regulating the long-term carbon cycle. Atmospheric CO2 dissolves in rainwater, forming a weak acid that erodes rocks. The carbon is then transported to the oceans, where it eventually becomes trapped in sediments. When these sediments are carried into the mantle by plate subduction, part of the carbon remains trapped there, while another part is released into the atmosphere by volcanism. This cycle maintains Earth's temperature within a range compatible with life for billions of years. Without this plate tectonics, CO2 would accumulate inexorably in the atmosphere, creating an uncontrollable greenhouse effect like on Venus, or it would remain trapped in rocks, gradually cooling the planet until total glaciation. Secondly, plate tectonics creates a diversity of habitats and ecological niches, from mountains, plains, and ocean trenches to continental plateaus, fostering biodiversity in all these forms. Thirdly, it recycles nutrients essential to life, bringing to the surface elements that would have otherwise been permanently buried in the depths. But what allows Earth to have plate tectonics? Well, it is a very specific combination of factors: a planetary size sufficient to maintain a hot interior, a precise amount of water to lubricate subduction zones, and a particular chemical composition of the crust and mantle. And you know what's fascinating? Well, estimates suggest that less than 5% of Earth-sized rocky planets could potentially develop stable and long-lasting plate tectonics. Our probability continues to drop. Let's now move on to the Earth's magnetic field. Our planet has a liquid outer core, composed mainly of molten nickel and iron. Convection movements in the core, combined with Earth's rotation, generate a powerful magnetic field, a phenomenon called the dynamo effect. This magnetic field creates a protective bubble around our planet, the magnetosphere, which deflects charged particles from the solar wind and cosmic rays. Without this protection, radiation would have gradually stripped our atmosphere, as happened to Mars, and bombarding the surface with deadly radiation for most complex life forms. To maintain a powerful and stable magnetic field over billions of years, a planet needs a liquid metallic core of adequate size. It needs a sufficiently fast rotation and a sustainable heat source to maintain convection. This is still a very specific combination of factors. Imagine for a moment, Mars likely had a magnetic field early in its history, but it died out when its core cooled. As a result, its atmosphere was gradually stripped away by the solar wind, turning a potentially habitable planet into a frozen desert. Let's estimate that only 10% of Earth-sized rocky planets can maintain a powerful and stable magnetic field over billions of years. Now, we are at less than 1/10,000,000th of our initial probability. We still haven't addressed other crucial points like the water cycle or even the atmospheric composition. Let's start with water. Our planet is often called the blue planet, and for good reason. About 71% of its surface is covered with water. This abundance of liquid water is extraordinarily rare in the universe. Even in our solar system, water exists mainly as ice, a bit like on Europa or Enceladus. Liquid water is the universal solvent of life. All biochemical reactions we know of occur in aqueous solution. Water transports nutrients, eliminates waste, and allows the diffusion of molecules necessary for biological processes. Without liquid, life as we know it would be impossible. But what is truly remarkable is the Earth's water cycle. Water evaporates from the oceans, forms clouds, falls back as rain or snow, runs off over the continents, and eventually returns to the oceans. This cycle constantly purifies water and redistributes it across the entire planet, creating diverse, habitable environments. Every raindrop that falls on your face is part of a cycle that has lasted billions of years, a cycle that has allowed life to thrive on our planet. But to maintain this cycle for billions of years, a planet needs a very precise combination. The combination includes temperature, atmospheric pressure, gravity, and topography. Too much heat, and all the water evaporates into space like on Venus. Not enough, and it remains frozen like on Mars. Gravity too weak, and water vapor escapes into space. Gravity too strong, and the atmosphere becomes too dense. The amount of water on Earth is also just perfect. With a little more water, the planet would be entirely covered by ocean, with no emerged continents. With a little less water, deserts would dominate, and the hydrological cycle would be compromised. This immense amount of water is probably the result of a delicate balance. This balance lies between the initial supply of water from asteroids and comets and losses due to various geological processes. It is estimated that only 1% of rocky planets in the habitable zone have the exact amount of water to maintain a stable hydrological cycle for billions of years. But now, let's move on to the carbon cycle, which is equally crucial. Carbon is the fundamental element of all organic chemistry and therefore of life as we know it. On Earth, carbon constantly circulates between the atmosphere, oceans, soils, and the Earth's crust. Atmospheric CO2 is absorbed by plants for photosynthesis, then passed on to animals that consume them. When these animals die and decompose, some of the carbon returns to the atmosphere or oceans, while another part can be buried in sediments, eventually forming fossil fuels. As I mentioned when talking about plate tectonics, this cycle acts as a planetary thermostat. When the temperature rises, the weathering of silicate rocks accelerates, trapping more CO2 and cooling the planet. When the temperature drops, this process slows down, allowing volcanic CO2 to accumulate and warm the planet. This negative feedback mechanism has kept Earth within a temperature range compatible with life for billions of years, despite a 30% increase in solar luminosity over that period. It's an incredibly precise balance for such a cycle to work effectively. A planet needs a very specific combination of plate tectonics, volcanic activity, continental landmass, ocean, and an active biosphere. It's a dizzyingly complex system where each component depends on the others. If we estimate that only 1% of planets with a stable water cycle also develop an effective, self-regulating carbon cycle, our probability drops further. We are now at 1/1,000,000th of a billionth of our initial probability. To give you an idea of what that represents, it's like having to find a specific grain of sand among all the grains of sand on all the beaches on Earth. And that blindfolded. And the craziest thing is that we haven't even touched on other crucial factors like the tilt of Earth's axis, the rotation speed, the precise atmospheric composition, long-term climate stability, and other elements. If we were to include these additional factors, our probability would drop by several more orders of magnitude, reaching 1 chance in 10 quintillion now. There you have the statistical revelation I promised you. Astronomers estimate there are about 10 billion galaxies in the observable universe. Each contains on average 100 billion stars. If we assume that on average each star has one planet, that gives us 10 to the 21st power. That is 1 billion billion planets in the observable universe. The inverse of this number, that is 10 to the minus 21st power, that is 1 chance in 1 billion billion. Do you see where I'm going with this? Our probability calculation led us to a number of the same order of magnitude as the inverse of the total number of planets in the observable universe. In other words, The probability that all these necessary conditions for a planet to host life are met, and if so, it corresponds approximately to the probability that it happens only once on a single planet in the entire observable universe. That planet is ours, Earth. Of course, these calculations have uncertainties. Perhaps some of our factors are a little too pessimistic. Perhaps there are many other planets that can host life. Perhaps even the universe is infinitely larger than the observable part, which would increase the chances of finding a habitable planet. But even taking these uncertainties into account, the conclusion remains stunning. We may be alone, not only alone in our galaxy, but perhaps even alone in the entire observable universe. This perspective can seem frightening, dizzying, even depressing, being alone in a vast cosmos. But I invite you to see things differently. If we are indeed alone, that makes our planet and the life it harbors something infinitely precious. This perspective changes. Radically, our relationship to our planet, Earth, is not just a home. It may be the only refuge of life in an otherwise sterile and indifferent universe. Every species that goes extinct is not just a local loss, but probably an irreparable cosmic loss. Our responsibility towards this planet then takes on an almost sacred dimension. We are not simply destroying our habitat, but perhaps compromising the only planet that harbors life. Paradoxically, this cosmic solitude can bring us closer to one another. We are all aboard the same spaceship, a tiny pale blue dot in the black vastness, and we have nowhere else to go. Our differences seem quite trivial in the face of this reality.